All right, Chapter 5, Part 2. Now we're going to talk about elasticity. You are familiar with elasticity, whether or not you really know it or not, because you've played with springs, you've played with rubber bands, you've played with all kinds of materials that are elastic, right? And that's sort of where we're going to start. If you want to look and see how much does the length of a spring change, right? So when I pull on a spring with some force, when I pull on a spring with some force, there's this constant K here that is the spring constant. And the change in length of the spring is proportional to the force divided by the spring constant. Or, your force gives you a certain change in length based on the spring constant, right? And the spring constant is in newtons per meter. So you're accustomed to thinking of this in terms of springs, and you'll probably play with some springs at some point in the lab here. So different types of some springs are stiff, right? A big thick spring would be stiff. A thin little spring would not be very stiff. That means the constant K is bigger for this one and smaller for the thin one. So this is the basics of Hooke's law. So if I told you, hey, I've got a spring and I put 1 Newton of force on it and it changes by 1 meter, that means the spring constant is 1 Newton per meter, right? Well, when we look at elasticity of materials, Hooke's law applies down in this area right here. You can go past that point and materials can sort of recover, right? They get a little fatigued, but they can recover. And then they have this place where you go too far, they deform. You will see that you may see that students have done that with some of our springs that we have in the lab. And you've done this yourself, right? You've pulled on a spring so hard at some point where it bent a little bit and would no longer go all the way back. Or you've pulled on a rubber band and stretched the rubber band out, or stretched the waistband in your pants out so much it wouldn't go back to where it really started. But the other thing about elasticity is it actually applies to almost everything, right? So when I push down on a desk, right, and I add a force to the desk, the legs actually get just a little bit shorter. All right, they get just a little bit shorter. And so when we talk about this, we talk about what we call Young's modulus. And the formula, right, the formula is the force per unit area. Right, force per unit area I'm pushing down with, or I can even be pulling up with a certain force per unit area, is proportional to Young's modulus times the change in length over the original length. L naught is your length when no force is applied. So when I push down on the desk, right, when I push down on the desk, the leg has force on it, and the leg gets just an itty bitty bit shorter, right? It doesn't get skinnier like I've drawn it, it just gets shorter. In A is the cross-sectional area. A is the area of this end right there, right? The area that the force is being applied to. The force is the force you're doing. Young's modulus, another thing that we have to just measure, right? Young's modulus is a constant. We have to measure it. You're not going to be able to unless you're given everything else in this form. You're not calculating it from any fundamental principle. Just has to be measured. Delta L is the change in length, right? And then L naught is the original length of the object. So, and when we do this, we talk about two different things. We talk about stress. Stress is force per unit area. That's what stress formally is. Yes, I know. You're stressed about the next exam. Stress is force per unit area. It's kind of like that. Strain is a change in length divided by the original length, right? That's strain. So stress is force per unit area. Strain is delta L over L naught. And then stress equals Young's modulus times strain. All right? Stress is Young's modulus times strain. That's really just going back to this equation right here. Stress is Young's modulus times strain. There's another modulus we'll put out there we call the shear modulus. And it's written kind of funny here. I don't know why it's written kind of funny here. Need to fix that. Okay. It really kind of has the same form, right? You can write it as F over A equals the shear modulus times delta X over L naught. Now, here's the difference with the shear modulus, right? Delta X is in a different direction from L naught, right? L naught is up and down. Delta X is perpendicular to that. Here's the other thing. The area A is here, but the force is applied this way, right? So shear modulus is a little bit different. Shear modulus is for what happens where we sort of end up twisting things and torquing them sideways like this bookcase, right? So again, shear modulus, we have to just find that out experimentally, and we've got still the stress, right? And stress is the shear modulus times, in this case, the shear, not the strain, right? Times the shear. All right. And then the last one we're going to hit is the bulk modulus. And again, we could write it in a way similar to, we could write it very similar to the other two. We could do F over A, right? A very bad A. F over A is our bulk modulus times delta V, that's a V, over V naught, right? So pressure, F over A is pressure, it's also stress, right, is the bulk modulus times delta V over V naught. One thing about the bulk modulus is the bulk modulus in this case is newtons per square meter, and you can see, you're trying to and it's always newtons per square meter because you got newtons per square meter and force over area, right? So all of these are newtons per square meter. Bulk modulus is, I'm now pushing inward everywhere on this surface. How much does the volume decrease? Or it's pushing outward. We're pushing outward in some way. How much does the volume increase? Again, Young's modulus, shear modulus, and bulk modulus are not things that you can know in any way other than running an experiment and finding them out that way. So we have tables. We have tables of Young's modulus, shear modulus, and bulk modulus. All right. We have tables where you just go look it up, and you look and you can see that, okay, aluminum is more compressible than, say, less compressible than, say, bone, right? And you'll notice that bone compressing and bone stretching are different, right? So you have to take that into account. Concrete, glass, all these different materials we have. Nylon, you can see, is somewhat stretchy, right? Nylon is stretchy, but we knew that already. Whereas iron, not stretchy, right? Iron isn't stretchy. Other thing you have to pay attention to on these charts, and anytime you're looking up anything in a chart like this, right up here at the top, you have the units, right? And so you always have to pay attention to what are the units I'm being given, because down here they just give you the base number, but this is, times 10 to the 9th. So whenever you're grabbing anything out of a chart, right, that's a really bad 9. Whenever you're grabbing anything out of a chart, look up above, make sure you know your factor of 10 and your units, newtons per square meter. All right, that's it for part 2 of chapter 5, and that's it for chapter 5.